Hello students, welcome to EPG Pathshala. I am Professor Pankaj Madan from Faculty of Management Studies, Gurukul Kangadi Vishwavidyalaya in Haridwar. Today we are going to talk on module Hypothesis Testing and Decision Making under the paper Quantitative Techniques for Management Decisions. After the completion of this module, the student will understand the hypothesis testing, the conditions for using the distribution in testing hypothesis, standard error, procedure in hypothesis testing, errors in hypothesis tests, and concept of one sample t-test. Setting up and testing hypotheses is an essential part of statistical inference. In order to formulate such a test, some theory is to be put forward, either because it is believed to be true or because it is to be used as a basis of argument, but has not been proved yet. For example, claiming that a new drug is better than the current drug for treatment of the same symptoms, or a claim of a chamber of commerce about the mean household income, we need to make a hypothesis. In each of the examples stated here, the question of interest is the two competing claims or the hypothesis between which we have to make a choice. The null hypothesis denoted as HO against the alternative hypothesis denoted as H1, or sometimes it is also denoted as HA, that is alternative hypothesis. These two competing claims or hypotheses are not, however, treated on an equal basis. Special consideration is given to the null hypothesis because null hypothesis is usually made on the basis of a literature review or a survey or the past experience or knowledge. A hypothesis is a claim, a statement, or an assumption regarding the population parameter that may or may not be true, but it needs to be verified by a random sample from a single population or two different population, or even it can be from sample can be from multiple populations. Now we have different situations, or we can say we have two common situations. The first is the experiment that has been carried out in an attempt to disapprove or reject a particular hypothesis, the null hypothesis. Thus, we give that one priority so that it cannot be rejected unless the evidence against it is sufficiently strong. Suppose a company makes a claim. Let's say Mahindra Scorpio, a car by Mahindra, they makes a claim that their mileage is 12.5 kilometers per liter for Scorpio. For that, we need to make a null hypothesis that HO, mileage of Mahindra Scorpio, is 12.5 kilometers per liter against the alternative hypothesis that mileage of Mahindra Scorpio is not or less than 12.5 kilometer per liter. If one of the two hypotheses is simpler, we give it priority so that a more complicated theory is not adopted unless there is a sufficient evidence against the simpler one, or we can say that the simpler one should be put as a null hypothesis. For example, in this case, it is the mileage of Mahindra Scorpio that has been put in a simpler way is 12.5 kilometers per liter. But in most of the cases, when it is not claim, rather it's an assumption or a statement, null hypothesis is considered negative or null. Null means no relationship. So most of the time, if it is not a claim, we put null hypothesis as a negative statement. In this case, it is different. The population here is the Mahindra Scorpio cars, and sample taken is from a single population. That is why we are saying that it is an example of a single assumption of a single population test, because we are taking only a sample of Mahindra Scorpio cars. The hypotheses are often statements about population parameters like expected value and variance. For example, HO might be that the expected value of the height of 10-year-old boys in the Indian population is not different from that of a 10 years old girls. This may be done by comparing two populations, the boys and girls. So here I mean to say that here we are making a hypothesis testing or assumption of comparing two populations. So we can talk about a hypothesis for a two population test, boys and girls. The hypothesis might also be a statement about the distributional form of a characteristic of interest. For example, that the height of 10 years old boys is normally distributed within the Indian population. A null hypothesis is denoted by HO, read as HO or H naught, and an alternative hypothesis is denoted by HA, read as HA, or sometimes we write it as H1. So H0, H1 or HO, HA. Both HO and HA are claims and counterclaims regarding a population parameter, and we test HO against HA. The outcome of a hypothesis test is reject HO in favor of H1, or do not reject HO, or we can say do not reject null hypothesis, which is again called as a alternative hypothesis. In hypothesis testing, whenever we have a decision to make about a population characteristics, we make a hypothesis. For example, mu is greater than 50 or mu is not equal to 50. Suppose we want to test the hypothesis that mu or the mean is not equal to 50. Then we can think of our opponent suggesting that mu is equal to 50. We call the opponent's hypothesis the null hypothesis and write it as H naught or HO m, or we can also write here as mu is equal to 50. And we make our own assumption or our own hypothesis as an alternative hypothesis. So in that case, we will write H1 colon mu is not equal to 50. For the null hypothesis, we always use equality, since we are comparing mu with a previously determined mean. For the alternative hypothesis, we have the choices of using less than or greater than or not equal to sign. Now, tagging the two competing claims regarding a parameter as null hypothesis or H1 or HA, the alternative hypothesis, is a matter of semantics, and it does not affect the final decision on which claim is accepted and which one is rejected. Means if HO is accepted or HO is rejected, or alternative hypothesis is accepted. That most of the time the students get into the problem of deciding that which test has to be used in which situation. So for that, I have made this table, and from this table you can see that there are two conditions. In one condition, when you are testing, and this test is about the means, and when you are testing the hypothesis about the means, and the sample size is more than 30, and the population standard deviation is known, or when the population standard deviation is not known, in both the cases you have to use Z table or the Z test. But I may like to caution you that when you use SPSS or a statistical software, they do not show or they do not use the Z statistics or the Z table. Most of the time, they use the T table or the T statistics. On the other hand, if the sample size is less than or equal to 30, and we assume that the population is normally distributed, then in that case, the population standard deviation is known, you can use Z table. But if the population's standard deviation is not known and the sample size is less than 30, then you have to use T test for hypothesis testing. Suppose you don't have a standard deviation of a population, and when the population is very large, normally it is difficult to collect the data or to find out the standard deviation. In that case, for the convenience, or when you use the sample and you compute your hypothesis testing based on not the population but based on the sample, in that case the standard deviation of the sampling distribution or the distribution of the sample status is called the standard error. Or theoretically, you can understand that there is more chance of an error when you are testing based on the sample rather than the population. So you can see here, instead of using the population standard deviation, you use the standard error. And the standard error formula is sigma x bar is equal to sigma upon under root x, where x is the sample size. When x is large, the probability of sample value of the statistics deriving from its mean by more than 3 times its standard error is very small. We therefore apply this formula to find out the degree of reliability of the statistics when inference drawn about the population based on the data of a sample. Consequently, the determination of standard error of statistics is a matter of importance in the sampling of large samples. How do you use this standard error? And its use, you can use this standard error to test the given hypothesis. It also provides an idea about the unreliability of a sample. However, in case of different distribution, you find out the standard error with a different formula. Like to determine the limits within which the parameters are expected to lie, standard error of a binomial distribution is under root npq, where n is the size of the sample, p is the number of success trial, and q is the number of failure. Now let's see the procedure for hypothesis testing. When we test a hypothesis, we proceed in the following manner. First, formulate the null hypothesis and alternative hypothesis, as I have told you through my previous slides, that we make HO and H1. Then choose a level of significance. And what is the level of significance? If the difference between it is the difference between the hypothesized mean and the sample mean, and it can be 5% or 0.05, then the value of alpha or the value of level of significance is equal to 0.05 or alpha is equal to 0.05. If nothing is mentioned, then take alpha, or it is convention to take alpha as equal to 0.05. The next step is determine the sample size. Say, and it can be same as the confidence intervals. Then you can collect the data, or if data is given to you, then you can calculate the Z or the T score with the help of a formula. Then utilize the table to determine if Z calculated or T calculated score falls within the acceptance region. Z table or T table is the cutoff point against which the test statistic value, and what is the test statistic value? Z calculated or T calculated or even delta is compared, and it is this table value is also known as the critical value for the test statistics. And when we test the hypothesis, we put the value, calculated value, before or after the critical value. And what is the critical value? The critical value is the table value. And this value we get from the Z or the T table, and usually these values are shown in the Z and the T table at the end of the most of the statistical books. So you can get these values from there and put them on the graph. They act as a critical value. Now then you decide that whether to accept or reject the null hypothesis. So first condition is reject the null hypothesis and therefore accept the alternative hypothesis. Or if you fail to reject the null hypothesis, then there is not enough evidence to suggest the truth of the alternative hypothesis. Now in the this chart, you can see that it summarizes the hypothesis testing techniques which I have discussed earlier for a single population. The null hypothesis is rejected, and when it is in fact true, that is, HO is wrongly rejected. The assumption was correct, but you have wrongly rejected the basic or the null hypothesis. For example, in a clinical trial of a new drug, the null hypothesis might be that the new drug is no better or average than the current drug, and you reject that null hypothesis wrongly. You can see that you make the null hypothesis there is no difference between the two drugs on average. The type 1 error occur if we concluded that the two drugs produced different effects, when in fact there is no difference between them, and that is what we have assumed. But type 1 error says that you have wrongly rejected the null hypothesis, saying that there is a difference between the two drugs, and that is what it shows as a type 1 error. You see the summary of both type of errors, and we will come back to this slide or discuss on this slide also after we discuss the type 1 and type 2 error both. But looking at this slide, you can easily judge or you can easily conclude that the type 1 error is when you wrongly reject hypothesis, null hypothesis, and type 2 error says when you wrongly accept or you don't reject the null hypothesis. So if you see the type 1 error, it is often considered as more serious and therefore more important to avoid than the type 2 error. Means that we need to avoid type 1 error, means wrongly reject the null hypothesis rather than accepting it, and you have to avoid that. The hypothesis test procedure is therefore adjusted so that there is a guaranteed low probability of rejecting the null hypothesis wrongly. This probability is never zero. This probability of a type 1 error can be precisely computed as a probability of type 1 error with a significance level alpha. The exact probability of type 2 error is generally unknown. If we do not reject the null hypothesis, it may still be false, and we call it as a type 2 error. As the sample may not be big enough to identify the falseness of the null hypothesis, especially if the truth is very close to the hypothesis. It means that for any given set of data, type 1 and type 2 errors are inverse related. The smaller the risk of the one, the higher the risk of the other. The type 1 error can also be referred to as error of the first kind and type 2 as the error of second kind. Let's talk about type 2 error. In a hypothesis test, a type 2 error occurs when null hypothesis HO is not rejected when it is in fact false. For example, in a clinical trial of a new drug, the null hypothesis may be that the new drug is no better or average than the current drug. So, what is the null hypothesis? There is no difference between the two drugs or on an average. So, the type 2 error would occur if it was concluded that the two drugs produced the same effect. Means there is no difference between the two drugs on average, when in fact they are produced different ones. Type 2 error is frequently due to sample sizes being too small. The probability of type 2 error is generally unknown, but it is symbolized by beta and it is written as P type 2 error is equal to beta. The type 2 error can also be referred to as an error of second kind. Now, we will show you what is, or will tell you what is type 1 error. We see a one sample t-test or a single population t-test. A one sample t-test is a hypothesis test for answering questions about the mean, where the data are a random sample of independent observations from the normal distribution n with mu and mu as mean, and sigma or the variance is, you know the mean, but variance is unknown. You can see that the null hypothesis of one sample t-test is mu is equal to mu o, where mu o is unknown. That is, the sample has been drawn from a population of a given mean and unknown variance, which therefore has to be estimated based on the sample or from the sample. The null hypothesis HO is tested against one of the following alternative hypotheses or depending upon the question posed, and that can be if H1 is mu and which mu is not equal to mu o, or mu is greater than mu o, or mu is less than mu o. So in this you can say that the sample is either rejected or it is accepted, and based on that sample study, you can either accept the hypothesis or you can reject the hypothesis. Let's take a practical question. Let's take a retail shop in a mall that has a target customer footfall of 50 people, but a standard deviation is not known. The sample measurements of the customer that visit this shop in a day are 45, 54, 51, 47, 52, 50, 41, 51, 43 and 50. It means that in this question, the HO mu is equal to 50. We are assuming that on an average, 50 people visit this retail shop, and this is our null hypothesis. Since we are talking only about the people visiting this retail shop, we can say that this is a single sample or a single population t-test. And in this case, the alternative hypothesis is mu is less than 50. Or you can say that the people visiting, the other assumption, the alternative assumption or the alternative hypothesis is that the people visiting this retail shop are less than 50% visit this shop. And the null hypothesis says that 50% or 50 people visit this retail shop. We are testing this hypothesis with alpha is equal to 0.05, or what we can say that we are testing that this hypothesis at 95% level of significance, that chances of correctness of this hypothesis is being tested at 95%. Since sigma is not known, or we will make use of sample standard deviation. Since the population standard deviation is not known, and we have taken in this example the number of people visiting per day, and we have taken a sample of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 days. So 10 days sample we have taken, in which we see on the first day 45 people visiting this shop, next day 54 people, and like that. So we will take the standard deviation of not of a population because it is not available, rather we are taking the standard deviation of a sample. And when you calculate this, it comes out to be 4.45. Finding out the mean, 48.7 is the mean, and then we go and find out the standard deviation of the sample, which comes out to be 4.45. Now putting this into the t statistics formula, t is equal to x minus mu over sigma. But in this case, as I have told you in my previous modules, that in this case we will not consider the standard deviation as a denominator, rather we will take standard error in the denominator. Why? Because in this case we are taking sample as a reference for testing our hypothesis, sample data, not the population data. So the chances of error is there. So we will use the standard error formula, that is sigma upon under root n, and sigma is 4.45, the sample size is 10. So in the denominator you can see 4.45 upon under root 10. So it comes out to be minus 9.24. Now to test the statistics or test hypothesis, t-test, this we have calculated, the t calculated. This value 9.24 is t calculated. We need to find out now the t table value, and that can be calculated from, or that can be seen from the T table, which is usually given as an appendix in most of the statistical book at the end. So from the T distribution table, the value of T at 0.05 alpha, the degree of freedom becomes n minus 1. That is 10 minus 1, it is 9, and it comes out to be 1.833. And since the table value, which is 9.24, is less than 1.833, so we reject the null hypothesis, stating that since the calculated value T calculated is minus 0.924 falls in the acceptance region, HO is accepted at 5% level of significance. Students, let's now summarize what we have learned in this module. This module provides an opportunity to the students to develop an understanding about the basic concepts related to the hypothesis testing, because it is an essential part of statistical inference. It is related to statistical estimation. Hypothesis testing consists of decision rules which are required in drawing probability inferences about the population. Mostly we use the hypothesis testing to prove the null hypothesis or the alternative hypothesis. In order to formulate such a test, usually some theory has been put forward, either because it is believed to be true or because it is to be used as a basis of argument, but has not yet been proved. Like claiming that the mileage of a new model of a car is better than the existing model for the same traffic conditions. So either it will be true or it will not be true. But to find out whether the said statement is true or not, the hypothesis is being formulated. In most of the business problem, before framing the two competing claim hypothesis between which we have a choice, the null hypothesis denoted as HO or H0 against the alternative hypothesis denoted as H1 or HA, we need to check the past data or facts of the business situations or the literature or the survey. Although these two competing hypotheses are to be treated on equal basis, yet special consideration is given to the null hypothesis that is framed based on experience or facts. So thank you very much for listening me patiently.